Tom Park from Berry Consultants, and in this video I'm going to show you an example of simulating a simple trial where we compare two treatments against control using our FACS trial simulation software. Okay, so in this example we're going to look at a FACS core design. I've just started FACS. Here we have, as usual, the FACS opening screen, and we again have here down the left-hand side the list of different possible types of design that FACS can help us with. And so this is going to be a FACS core design with a dichotomous endpoint. If we double click on that option, FACS will load itself up with the right set of screens for entering the parameters for this kind of design. We have across the top the main tabs which correspond to the different types of parameters we need to enter. The study tab has the parameters for the principal structure of the design that we're going to be entering. Then the virtual subject response tab, where we'll set up the different scenarios of how subjects might respond to the treatments. Then the execution tab covers things like how quickly we'll accrue subjects and how likely they are to drop out during the trial. And then we start to enter the design aspects of the trial. The first tab is where we specify what we call the quantities of interest. What are the values that we want calculated, both during the trial and at the end of the trial. And then we have the design tab where we specify how we're going to want those quantities used in terms of making our decisions. So we're going to start here on the study info tab where we start to specify what kind of study this is we're designing. So it's going to be non-adaptive, and we're not going to use longitudinal modeling, and subjects are going to be complete after 4 weeks. So 4 weeks from randomization, we will have the final response of our subjects. Have they responded or not to the treatment? We're going to recruit subjects continuously, and we've done a little sample size calculation which says we need 52 subjects per arm. We're going to have a control and 2 treatment arms, so we're going to say total sample size is 156 subjects. And we let FACS know that actually responses are a good thing, and what we want to see is higher response rates. The treatment arm tab we simply set up with our control arm, which we can toggle on and off up here, and we're going to add 2 different treatments which we're going to compare to control, and we'll just simply call those treatment A and treatment B. On the subject responses, what we have is we're going to set up a number of scenarios in which we're going to test our design's ability both to control type 1 error, to detect a response when there is one, and to select between the 2 treatments when they both have a certain degree of response, but one is better than the other. Now, across the scenarios, we're going to consistently enter the expected response rate on the control arm of 0.35. And so in our very first profile, it's going to be our null example, which we're going to use to check the design's control of type 1 error. And so the response rate on all the arms is going to be 0.35. Now we'll enter 2 scenarios where one of the treatment arms has a response, and it's going to be treatment arm B in one of them and treatment arm A in the other. We're just going to mix things around to make sure the design isn't particularly biased to one or the other. So in the first of these, B55, the control will still be on a response rate of 0.35. Treatment B is going to be the effective one, so treatment A is still 0.35, and treatment B has a response rate of 0.55, and that's one that we would want FACS to successfully choose, or our design to successfully choose. Then we have one where the A arm has a good response, and it's even better than the previous one. Then we can have one where they're both at 5.5. So either of those would be a good choice. We can have one where B is at 5.5 and A is done even better at 6.5. And here, although B has got a reasonable response, A clearly has the much better response, and what we want is to be able to pick treatment A. And I think that's going to be enough scenarios for now. Of course, we could introduce greater variability, testing other response rates, 0.45, 0.6, and so on, to test how sensitive the design is to changes in the actual response rate. The execution for this particular example is going to be quite simple. We're going to say we're going to simulate just a simple mean accrual rate throughout the trial of 6.5 subjects per week, so about 26 subjects every month, and we're not going to simulate any dropouts. So that's set up our puzzle, if you like, the constraints of the design, the target of the design, the different scenarios our design has to be able to function over, and now we start to specify some of the design elements. So in this trial, the requirement is to have make a decision based on a p-value. So we will use handle missingness with LOCF, although we're not simulating any missingness. And we're going to use a simple Bonferroni adjustment to take care of the two arms. At this point, we're not going to bother to predict the probability of success in a future trial, or even do any Bayesian posterior probabilities. And we can forget targets like minimum efficacious dose and ED90. What we do need to add is what we call a decision quantity. So that takes one of the quantities we are computing, in this case the p-value, and we're going to make decisions based on the treatment arm with the smallest p-value, the one that has performed best. So that completes our quantities of interest, and now we can start setting up the design and how we're going to use that. The dose response is a Bayesian model for analysis, which actually isn't going to feature at the moment because we're just doing the p-value calculations, but we'll set it up for future use. So we're going to do just a simple pairwise comparison. So the Bayesian is going to be very similar to the frequentist analysis with a largely non-informative prior. The prior in facts for the Bayesian analysis of a dichotomous endpoint is done in the log odds space, so it's a normal prior, and we can see what the shape of that distribution looks like over here on the prior graph. It looks a little bit sort of like a bicuspid, but this is actually in the log odds, in a normal distribution in the log odds space. It's as close as you can get to a sort of a flat beta distribution. We're not going to be doing any additional frequentist analysis. We've got our p-value set up in the QOI. We'll be using that. And we're going to initially have a simple equal allocation with a block of 6, so allocating 2 subjects to control, 2 to treatment A and 2 to treatment B. And then finally, we simply set up as the success criteria where we test the p-value using the treatment arm with the smallest p-value, and of course would be nice and traditional, and we'll require that to be less than 0.025. And if you like, we can also set the converse decision for futility. So now we're ready to roll. We can do our very first simulations. At this point, I'll just run up, for the sake of speed, I should just run 100 simulations of each scenario. But you can see we get those done in almost less than a second for each scenario. So our probability of success in the null is 0.06, which looks like maybe the p-value isn't actually controlling the time when error the way we'd expect, but of course it's simply that we've done only 100 simulations, so the sampling variability, and we just happen to have gotten unlucky with the particular simulations and the particular data that's been sampled. As we run more and more simulations, we'll see that converge towards 0.025. You can see we've got fairly low power if the just one arm has a response of 0.55, but if one has a response of 0.6, then even with only our 100, with our possible sampling area, we see we're bang on the expected power of 0.8. And if both arms work, we've got a little bit greater power. The other thing we can look at is the probability of success and correctly choosing the right arm. So this was the checkboxes I was filling in as I created the scenarios. These checkboxes are not passed to the simulation engine so that it can cheat and pick the right arm. These are held back by the user interface so that it can, if you like, mark the results, a bit like a school teacher. And here you can see that in this scenario, although we have a nice high power of 84%, our probability that we were successful and we picked the correct arm A with a higher response rate, is actually only just over 70%. So one of the things we can do now is just to look at some simple modifications of this design. So one thing we might want to do is say, well, maybe we can improve the power of this design if we do a slightly different allocation ratio. Now we know if we've got two arms both being compared to control, a slightly biasing the allocation to control is a good thing and will get us more power. So we can easily change that. We keep everything else the same, and we're ready to get some more simulation results. Now here, because we're going to be doing comparisons of sort of small differences in type 1 error and power, we're going to have to do more simulations to get slightly more accurate estimates from those simulations. So here I'm doing 1,000 in each scenario. In the end, you'd probably be using 10,000, but there's no point going to 10,000 until you're reasonably confident that your design has iterated towards the right space. So we can see we're already sort of asymptotically approaching 0.025 here. The type 1 error is considerably less. Power we're seeing when one arm has a response of 55 is a little bit better. It's 0.44 and so on. But what we need to do is compare this with our even allocation, and that's some results I've already got. I'm going back and opening the original design, but this is a version that I'd already done and already simulated, in this case at 10,000 per arm, which is still quite quick. It's no longer than time to go and get a cup of coffee, but probably too long for you to bother to sit through during a video. And here we've now got even more accurate estimates of the type 1 error and power, and we can start to compare it with our design changes, in this case the change of allocation ratio. And what we find is that the change of allocation ratio has indeed increased our power very, very slightly. So it doesn't do quite such a good job of choosing between one arm with a high response rate and one arm with a low response rate. So here in the equal allocation, we can look at the response and target selection. So here we can see we've got a probability of just over 80%, perhaps 85%, selects the low dose, or treatment A, with the higher response rate. In the example with the 3:2:2 allocation, we tend to see very slightly, it's actually not that clear on this example, but a very slightly lower correct selection of the treatment A. The next feature I'd like to demonstrate is adding an interim for futility. So we save this design and we now add an interim. So we're going to add an interim at about halfway through the trial. So when we've recruited 78 of our 156 subjects. In order to do this, the trial has to be, I have to tell facts, I want to simulate an adaptive trial. That will start to add some tabs in for allow this additional complexity. And one of them is the tab where it allows me to specify when the interims are. So I'm going to specify, based on the number of subjects enrolled, I'm going to have an interim at 78 subjects. My allocation is still going to be 3 to 2 to 2. And now on my success and futility criteria, I've still got the final evaluation criteria, but I now have an additional tab where I can specify that I do something different at the interim, and here I'm going to stop for futility if things aren't going well enough. But at this point I haven't got the quantity of interest specified that I want to measure, and what I want to use is what we call a Bayesian predictive probability of how well this trial is going. So what is the probability if I do at the interim, if I look forward to how things might turn out, how I expect things will turn out based on what I've seen so far at the trial maximum, what is the probability I'm going to meet my p-value criteria? So I give it the same p-value criteria that I'll be testing at the end, but it's going to judge at the interim how likely I am to meet that. And this now gives me, I need to also make a decision QI. So I now have a decision QI that uses it, and obviously what I want to do is test the arm which has the best probability of success, and if that arm with the best probability of success still has very low probability that it will be successful at the end, say less than 10% probability that this trial will turn out successful, then let's stop this trial for futility. And I can now run a bunch more simulations. And what I'm going to be looking for is, in the null case, I'm going to want to stop for futility. So I'm going to want to see futility stopping, and I'm hoping to see an expected lower sample size. But then in my other scenarios where I've got some sort of response, I want to see only minimal stopping for futility, ideally such that it doesn't reduce the actual power of those scenarios. So running 1,000 simulations of each scenario has now taken a little longer to complete, perhaps about a minute, because FACS is now doing 2 analyses per simulation, so very roughly each simulation is taking twice as long as before. And the first thing we want to look at is, are we stopping for futility in the null case? Well, we are. We're stopping nearly 40% of the time, and that's giving us an expected mean sample size of 126. Obviously, that's a kind of a bivariate distribution. I've got nearly 40% of my simulated trials. I've got a sample size of 78, and then the ones that didn't stop earlier will have gone all the way to 156. The other thing I want to look at is how often do I stop for futility when actually I've got an effect, and although there is a little bit of stopping, perhaps a lot more when I've only got one arm and it's performing weakly, the actual amount of early futility stopping doesn't seem to have reduced my power materially. So we seem to have got a reasonably safe and conservative early futility rule, which has not reduced my power, and it will mean that if treatment isn't working, I've got a reasonable probability of being able to get out early. And then the last thing I want to look at is, if we look at some of these trials, so we can look at some individual examples. So here's one where we're looking at the case where we've got some effect in one arm and no effect in for the other treatment. And we want to look at, let's say, the p-value. If we step through it, we can see there's some cases where the treatment that doesn't work has done extremely badly. So in that case, we don't want to stop the trial because we've got an arm that's doing reasonably well. But why should we continue the trial and continue using treatment A? So rather than a futility decision, perhaps we can take kind of like a half futility decision where we drop the poorly performing treatment but carry on with the remaining one. So this is the last version of this design we're going to look at in this example, but it's quite nice. So we'll save it as, I'll add arm drop to the design title. As you can see, my titles of my fax files get longer and longer as I apply more features. And here, taking a copy effectively of the simulation design which had its interim at 78, and it was just stopping for futility. What I'm now going to do is, rather than just have a fixed allocation, I'm going to allow arm dropping. So that keeps the fixed allocation, but I now have a rule where I'm going to say if the probability of final success for this arm is less than, say, 0.05, so it's even more conservative than our stopping for futility, then we'll allow one arm to be dropped. And if they were both bad, we'll say, for sake of argument, let's drop the lower one rather than the higher one. And then we've got three options, and this depends on what we want, what our objective is of having this arm dropping. So one would be, well, that's great, we've only got one arm and control now, we won't need so many subjects, so we could finish a bit quicker and have a slightly cheaper trial, so we could decrease the study size. Another option would be to carry on to the full study size, but simply reduce the block. So, say we lost treatment A, we would now, instead of a 7-dose block, 3 to 2 to 2, we just have one treatment and control, so it'd be 3 to 2, so the block size would be 5. But as we've dropped an arm, we no longer need to keep preferentially allocating to control. So what we're going to do is we'll keep the study size, but we'll maintain the block size. But now both these slots of 2 for treatment A and 2 to treatment B will be allocated to the remaining treatment. And what we're going to hope is that that will result in slightly higher power in these scenarios where it's going to be quite likely that we're able to drop a poorly performing arm. So once again, we get to our simulations tab and we run 1,000 simulations of each scenario. So again, we've waited about a minute to get our 1,000 simulations of each of the 5 scenarios completed. We can see our early stopping for futility hasn't changed. We're still 40% in the null case and nice and small in the effective cases. And what we notice here is that our power in these 2 scenarios, where one arm doesn't work and the other arm does, has increased by about 5%, which is kind of what we would be hoping for. And we can also test here, we've faxed reports on the proportion of arms being dropped, and we can see in the case where treatment B has a good response, it is hardly ever dropped, whereas the other one is dropped nearly 36% of the time. And in the third scenario where treatment A works, it's hardly dropped at all, particularly even less because of course it's got better response, and the other arm is dropped nearly 40% of the time. So in round about 30 minutes, using fax, we've been able to set up a design, simulate it, and explore 3 variations of that design to see if those variations enable us to make a more efficient design, both using fewer subjects if the treatment is futile, and getting greater power by dropping a poorly performing arm in those scenarios where one of the arms doesn't work terribly well. I hope you enjoyed that demonstration. For more information and other videos, visit the Berry Consultants website. Thank you for watching.